Hello everyone, welcome back. In this video, we're moving on to public key cryptography. So we have 5 items to cover. However, in this particular video, we'll be looking at RSA. But firstly, we need to understand why we need public key crypto systems to begin with. So what is the problems of symmetric key crypto system? Well, when we talked about DES and AES, they're all symmetric key crypto system, which means when you want to encrypt something or decrypt, they both need to use the same key. Okay, but in a network, typically we have more than 2 users. So when you think about, say you have a chat app, you can communicate with multiple other users at the same time. So given n users, how many different keys do we need to establish connected between every pair of users? It becomes order n squared, right? So if you think about a fully connected graph, the number of edges between the nodes becomes n times n minus 1 over 2, which is in quadratic. So to establish a unique pair of keys for individual pairs, that's a very large number of keys to manage, and that's probably not an ideal thing to do. Okay, so that's when a public key cryptography system comes in handy. So what it does is we keep 2 different keys, one for encryption and one for decryption. So when somebody wants to communicate with you, then what they have to do is just find your public key, encrypt the data using your public key, and then give it to you. Okay, and then you can use the private key in order to extract the encrypted message. And usually the private key is only held by you. So that means you keep the private key safe away from everybody else, while your public key can be visible to everyone outside. So this means you don't need to create an n squared pair of keys. Instead, you only have to have one public key available. So the system looks like this. Alice is trying to send an important message, and Bob's public key is available from the directory. So you can look it up, what the public key is, and use that to encrypt the data. To decrypt, you have to have a private key, which only Bob holds. So that way, even if you intercept this ciphertext, you cannot decrypt using the public key again. Okay, so that's the handy part of using the public key crypto systems. And only Bob will be able to retrieve the plain text using the private key. Okay, and this can also be useful to validate your identity as well, which we'll see a bit later. But the story goes like this. Alice is going to encrypt a message using her private key. So because encryption decryption, the key pair works the opposite way. If you encrypt using your private key, then you can decrypt using the public key. And since public key is available to everybody else, but the private key is only available to that particular individual, so if Alice encrypts a confirmation message using the private key, and as an outsider, you decrypt using Alice's public key and you can see the message, then you know that the particular message is coming from Alice because only Alice has the private key. So that's the good thing about using public key crypto system. Okay. Like this. And in asymmetric key encryption, there's a few different methods of doing this, but it branches into 2 main parts. One is integer factorization problem, and the other one is discrete logarithm problem. We'll have a look at an example from both, but RSA falls into a integer factorization problem. Okay? So we'll look at RSA. So the question is like this. Given 2 large primes P and Q, what we can do is compute the product N, which is P times Q, And given n, how to get p and q? Okay, how difficult is it to get p and q? That's the question. Okay, so if we are given a bunch of integers like p, q, r, s, t, and the product is n, you multiply p, q, r, s, t, all of them together. Doing the multiplication is polynomial time. Okay, so that's quite straightforward. We can do this reasonably quickly or in a practical time. However, if you're given n and you want to produce values p, q, r, s, t, or any subset of those, you have to. There is no specific method that allows you to quickly factorize this, right? So the difficulty of doing this, the backwards, is non-polynomial, which means it's going to take much more effort and time for you to get those the product numbers. Okay. So that means given primes p and q, computing the product value n, it's easy. However, given n, trying to retrieve the prime values p and q, this is hard. And we are using this fact to construct the RSA type public key crypto system. Okay? So let's have a look at an example. Given 11 to the power of x mod 13 equals 9, okay, so we're given the product n, which is 9, and what is the value x? Okay, you can pause the video here and trying to calculate the value of x. Okay, assuming you have done so, I hope you got the same answer as me. But basically, the way we go about doing this is there's no particular way, so you can only brute force this. So trying from 1, eventually you'll get to x equals 8, and you'll find that 8 is the answer. Okay, so this was relatively simple because our values were really small. It's modular 13. Okay, but how difficult is it when p is, say, 512 bits, right? So 512 bits represent 2 to the 512 values, which is a very large number. Okay? So if you're brute forcing this, in practice, this is not possible to crack in any feasible time. Okay? And that's what the RSA is based on. So RSA is the first public key crypto system that has been introduced. It has been the worldwide standard for the last 30 years, ever since it's been introduced. And it's still going very strong, really. You can find its usage everywhere. RSA is named after its creators, Rivest, Shamir, and Edelman. So later, if you come up with a really cool idea about some crypto systems, you can name it after yourselves. Okay. To use the RSA as a public key crypto system, we do have some prerequisites to construct it. Okay. So we need to have good prime numbers, which are very hard to find or very large. We need to find the greatest common divisor. We need to know the Euclidean algorithm, relatively prime, congruence, and multiplicative inverse. Okay, so let's start with prime number. So if you are not familiar with the term prime number, it's basically the number that divides by itself or 1, okay, without any remainders. So hopefully that one is straightforward. For example, the example 13 was a prime number, 17 is also a prime number, 23 is a prime number, and so forth. Okay. And then we need to know how to calculate the greatest common divisor. Greatest common divisor is basically a largest whole number that can divide both a and b, where a and b are other larger integers. So example 45 can be constructed by 3 to the power of 2 times 5. On the other hand, 18 can be constructed by 2 to the power 1 times 3 to the power 2. Okay? So if we calculate GCD of 45 and 18, then the common factors between the two are 3 to the power of 2, which is 9. So 9 can divide both 18 and 45. Okay? Collecting the largest terms in between. So how do we calculate GCD? One way is to use Euclidean algorithm. So if you're not familiar with this, please do revise on it, as I don't really dig into details about Euclidean algorithm. But basically, given GCD of AB equals D, then the equation becomes quite simple, where A equals B times Q plus R, where Q is some quotient and R is a remainder. And given that equation, we can deduce that GCD of AB is equivalent to GCD of BR, which later will become D. So what's happening here is we're reducing A and B to the smallest term, and once they are no longer divisible to one another, then that becomes the greatest common divisor, value D. Okay? So what is the GCD of 33 and 18? I will leave you to calculate this. Okay? Otherwise, now once we know how to do GCD, we also need to know how to do extended Euclidean algorithm in order to find out what are the multiplicative factors that produce the GCD. That means there are two values, x and y, such that a times x plus b times y will result in D, which was the GCD between a and b. Here, the values x and y are not necessarily just positive values, they can be negative. And always one or the other is a negative value. Okay? So for example, if a equals 204, b equals 72, then what we want to find is find 204x plus 72y, which equals D. So the first thing is to calculate D. So you apply the GCD Euclidean algorithm to find GCD, and if you follow through, then the GCD becomes 12. Okay, so the working steps are there. So once we know 12, we can put that back into the equation, which is like this. So now we're going to reverse the calculation steps. So from here, we rearrange it such that it's 12 equals. Okay. So 12 equals, here, 12 equals 72 minus 60 times 1. 72 minus 60 times 1. And then 60 here can be recalculated by 204 minus 72 times 2. So we plug that in here in place of 62. And eventually, by replacing the values after expanding, you will end up with the terms a and b in the equation. And that's when you can stop. So here, x equals minus 1 and y equals 3 for this particular instance. Okay. So here's another example of GCD 89 and 64. And if you apply the Euclidean algorithm, these are the steps that you follow to calculate this. Okay. And eventually, you will have to reverse this. So here, you will convert this into 1 equals 3 minus 2 times 1. You will convert this into 2 equals 11 minus 3 times 3, and so forth. And once you have done that, you have to plug it back into the equation from above, right? So here we had 1 equals 3 minus 2 times 1, and 2 equals 11 minus 3 times 3. You expand this and collect the terms together, so this becomes 3 times 4 minus 11. So there's 3 3's here, and 1 3 here, and minus becomes plus, right? And then you keep repeating this until you end up with a term which you begin with values a and b. So 64 and 89 was our values a and b. Then our multiplicative factors are 32 and negative 23. Okay? So this will become very important later when we do multiplicative inverse. So just keep that in mind. Okay? So once we got that sorted, we can understand a few other things like relatively prime. So two numbers a and b are relatively prime if they have no common divisors greater than 1. So that means even though your number may not be a prime number, if your factors, there are no overlaps, then those two numbers are relatively prime. So example, a equals 8, b equals 15. Both have some divisors like 2 and 3. However, they don't have any common divisors, right? So 2 does not appear in this list. 4 or 8 does not appear in this list. Same with 3, 5, and 15. So here we can say that A and B are relatively prime. Okay. The next item is congruence. In modular arithmetic, congruence is having the same remainder when divided by a specific integer. So given n equals greater than 0, two integers a and b are congruent modulo n if a is equivalent to b mod n. So here's an example. 10 is equivalent to 1 mod 3 because you divide 10 by 3, the remainder is 1. So that means in modulo 3 clock, value 10 is equivalent to value 1. So they are congruent to each other. Similar with 12, 12 is equivalent to 12 mod 5. So we can say that 12 and 2 are congruent modulo 5. Okay, so those are just a few terms that we use later. Okay, so keep that in mind. And the last item is multiplicative inverse. Okay, so this is where we want to find x and y such that x times y is equivalent to 1 mod n. My slide is missing 1 there. So for instance, if n equals 10, so that's in modulo 10, we can see that 1 and 1, they are x and y, same value. But here, 3 and 7, they are multiplicative inverse in mod 10. 9 and 9, they are multiplicative inverse of mod 10. Okay. Out of this, you also have to remember that not all values will have a multiplicative inverse depending on the modulus number we're using. So here you can see that value 2 does not have any multiplicative inverse. Okay. So let's have a look at an example. GCD 60 and 37 equals 1. What is the multiplicative inverse of 37 mod 60? Okay, so that if I rephrase the question, what is x when 37 times x equals 1 mod 60 or equivalent to 1 mod 60? Okay, and if you remember our extended Euclidean algorithm, we can use that to calculate this. So here, your exercise is to calculate x. You can pause the video here and calculate. Okay, so assuming you have done that, if you follow through the extended Euclidean algorithm, you will find that x equals 13. Okay, so when you do 13 multiplied by 37, you actually get a much larger number than 60. But because we are working in modulus, all you have to do is divide that product value by 60 and use the remaining value as your actual value. So now you number fit between 0 and 60. Okay, so now that's all the terms and techniques we need to establish RSA encryption decryption system, right? So let's have a look how it works. Okay, so what we want to do is prepare a plain text, and Bob will have a public key, which is a pair of values e and n, where e represents a large number Bob provides based on his prime number, and n is our modulus value. Okay, with the Bob's public key, what we calculate is p to the power of e mod n, and that's going to generate our ciphertext C. Okay, so we can send over the ciphertext C, and what Bob does is Bob has its own private key, which is dn pair, and what it does is compute c to the power of d mod n, and with this process it retrieves back the plaintext p. So we can retrieve plaintext p this way. So the mathematics behind is actually quite simple, but if you're trying to crack this code, because we are doing the power operation, it's very difficult to do so. Just like how you try to guess 13 to the power of x mod something, what is x? Okay. So next question is, How can we generate those keys? Okay, so this is the most time-consuming part of one of the time-consuming part of RSA, in addition to computing the powers. Okay, so let's have a look. To generate the key pairs, we have 5 main steps. First one is to select 2 large primes, P and Q. And nowadays, you usually select something that is greater than 1024 bits. So once we selected P and Q, we can find the product value n. And this n is going to be our modulus value. Okay, and using P and Q, we also compute Euler's torsion function of n. Basically, it's a P minus 1 multiplied by Q minus 1. Okay. So once we computed phi n, then we pick an integer e, which is relatively prime to phi n. Remember, the relatively prime means they don't share any common divisors that are greater than 1. Okay? So once we calculated e, you can use that e as the public key. Okay? And the final step is compute d such that e times d is equivalent to 1 mod phi n. Okay? So once you calculate that d, then you have now public key and private key pairs. Okay? Probably should put them other way around, en and dn, like the example. But nevertheless, those are the 3 numbers you need to construct the public and private key pairs. Okay? So steps, hopefully, quite straightforward. So let's have a look. Here's an example, key generation. In practice, you choose large numbers, but for example, we will work with small numbers. Okay, so P equals 5, Q equals 11. So those both are prime numbers. Then we can calculate n equals P times Q, which is 55. Okay, phi n is P minus 1 times Q minus 1, so that becomes 4 times 10, so 40. So our phi n is 40. Okay, next we need to select E, and in this example, I have selected E equals 13. Okay, because 13 is relatively prime to 40 because 13 itself is a prime number. So if you select E, which is a prime number, then you will always guarantee that it will be relatively prime to phi n, regardless of what vectors phi n might have. Okay, and then using the extended Euclidean algorithm, you can compute E times D equals 1 mod phi n for value D. Okay, and in this instance, D equals 37. So if you do 13 times 37, it's going to give you a large number, but if you keep reducing it by 40, eventually you'll end up with value 1. Okay. So by following these, we now have public key En equals 13 and 55, and private key 37 and 55. Okay. Let's have a look at the encryption first. Okay. So now Bob wants to send Alice a secret message. Let's say the secret message is 13, 8, and 16. Okay. Bob uses Alice's public key to calculate the following. Okay. So public key is given, which is 13 and 55. So what you do is 13 to the power of E, which is 13, mod 55. This is will come out as 8. Okay. 8 to the power of 13 mod 55 will come out to 28. 16 to the power of 13 mod 55 will come out to 26. Okay, you should be able to trace these. So the sending values are 8, 28, and 26. So Alice receives 8, 28, and 26. Okay, so Alice now uses her private key 37 to retrieve the plain text. So 8 to the power of 37 mod 55 is 13. 28 power of 37 mod 55 will give you an 8. 26 to the power of 37 mod 55 is 16. Okay, and to show that that is actually the real value we calculate, here's the working for it. Okay, normally if you type this into the calculator, it's not going to be able to handle because there's too many digits. But you can do step-by-step calculations and solve this by hand. Okay, so when I ask you questions like this exam, don't write answer that, oh, my calculator can't handle this, because you can actually calculate this, all right? And following these steps. So for instance, 26 to the power of 37 is equivalent to 26 times 26 to the power of 36, right? And just like reversing the fast exponent, we're going to halve this, right? So we do 26 squared and then half the power. So it becomes 676 to the power of 18 mods 55. The good thing about modulus operation is I can reduce this value. Okay, so if I take modulus 55 from 676, it reduces to 16. Okay, so now it becomes 26 times 16 to the power of 18, which is equivalent to what we had before. So we repeat this process. So this becomes 256 to the power of 9, reduces to 36 to the power of 9. Since this power value is odd, I'll take one out here, and then it becomes 36 squared to the power of 4. So 36 squared, and then you reduce it, it becomes 31. And here, at this point, if you multiply these two together, it takes away. But these numbers should be quite small enough for you to work with. So it eventually reduces to this. And if you expand this and calculate it, it becomes 16, which is what we have here. Okay, so that was one. And that's the same one. Okay. So by following these steps, you should be able to do both encryption and decryption using small numbers. So make sure you can trace these yourselves with just a calculator, right, instead of using the online calculator which handles larger digits. Okay. So next question is RSA quick? Because we complained about triple DS being quick, right? And unfortunately, the answer is no. RSA is actually really slow. RSA requires many computations to carry out. This is mostly the power computation. So even the encryption is much, much slow. So there's a trade-off. We only need to provide one key to the public, which anybody can use to communicate without you disclosing the message to others. But in return, the speed is very slow. So use modular operations to reduce intermediate step results can kind of speed it up, just like reverse fast exponent computation. However, this is not sufficient to speed this substantially. You could also, so in second point is to use the fast exponent computation algorithm, CMath1721. However, those also have limitations. Okay. So there were RSA challenges like on the link there. Basically, people trying to find how quick they can crack RSAs, but it finished in 2007 with the growing computation power without people coming up with any new solutions to do so. So by 2009, RSA 768 was the largest subprime solved to date. And I was not able to find anything new, so if you find anything new, please let me know. But remember that RSA uses PQ both 1024 bits big. So by creating the product of those two, you will end up with 2048 bits minimum. So by only reaching up to 768 bits, we are still way off from cracking this. Okay, and nowadays for some more higher security requirements, the P and Q can start from 2048, which end up with over 4,000 bits to compute. All right, so that concludes the RSA video. Obviously, there are pros and cons to RSA, but I will cover this, the summaries a bit later. But essentially, what we want to do is use a combination of both public key system and private key systems, where public key system is used to transfer your private key to people who you want to communicate, and then use the private key encryption system, which is much faster to send a large quantity of data. All right, we'll stop here. Otherwise, I'll see you in the next video. Bye-bye.